This is a maze with 250,000 rooms. Every open square is a room. Every dark line is a wall. Somewhere inside it, there is a way from this corner to that corner. Today, 4 different algorithms are going to look for it. They all find a way out. The difference is how many rooms they open on the way, and that difference is enormous. By the end of this video, one of them solves a grid this size by opening 11,000 rooms. Another one opens 195,000. Same grid, same answer, 17 times the work. But there is a twist in the middle of this that I honestly did not expect. The clever algorithm, the one that is supposed to win, gets absolutely nowhere. So let's start as small as it gets. 3 rooms across, 3 rooms down, 9 rooms. We start in the top left, we want the bottom right. You can see the answer straight away. And that is exactly the point. Because a computer cannot see it. It is standing inside one room, in the dark. It can ask one question: which doors out of this room are open? It keeps a list of rooms it has reached, but has not looked inside yet. That list has a name. It is called the frontier. And this whole video comes down to one question about it. Which room do you take out of that list next? The first answer is the fairest one you could pick. Take the room that has been waiting the longest, first in, first out. That is a queue. It spreads outwards in a ring, one step at a time. Every room it opens is the same number of steps from the start. This is called breadth first search because it grows sideways before it grows deep. And it comes with a promise: the first time it walks into the exit, that is the shortest way there. Nothing shorter can exist because everything shorter has already been checked. The second answer is the exact opposite. Take the room you found most recently. Last in, first out. That is a stack. Now it does not spread out at all. It walks down one corridor as far as that corridor goes. When it hits a dead end, it backs up to the last junction and tries another door. This is depth first search. On this tiny maze, it opened 7 rooms. The fair one opened 5. 2 wasted rooms out of 9. That sounds like nothing. Hold on to that number. 10 across, 10 down, 100 rooms. The fair one grows a blob. The committed one draws a snake. But now look at the answer they came back with. It is the same route, not a similar route, the same one. That is not luck. That is the maze itself. A maze like this one has no loops anywhere in it, which means between any 2 rooms there is exactly one way to go. So finding a way out and finding the best way out are the same job. So the contest is about one thing only: how much work you waste to get there. Now, our first 2 algorithms have no idea where the exit is. But we know where the exit is. It is the bottom right corner. So let's hand that over as a hint. From any room, count the steps to the exit as if every wall had been deleted. That number is a guess at how far there is still to go. And it is never too big because a wall can only make a trip longer. That kind of guess has a name. It is called a heuristic. The third algorithm is the greedy one. It always takes the room with the smallest guess. It simply runs at the exit. The fourth one is the A-star algorithm, and it is the famous one. It adds the steps already taken to the guess about the steps still to come. So it chases the room on the most promising complete route, not the room nearest the exit. And here is the part I find genuinely beautiful. All 4 of these are the same program. Same loop, same frontier. One line is different. The line that decides what comes out of the list next. Sort by the steps already taken and you have the fair one. Flip the sign on it and you have the committed one. Sort by the guess instead and you get the greedy one. Add those 2 together and you get the A-star algorithm. 4 famous algorithms, 1 program, 1 line, 50 across, 50 down, 2,500 rooms. all four at once on the same maze. The routes are identical, exactly as promised. 743 rooms long. The work is not identical at all. The greedy one opened 968 rooms. The fair one opened 1641. So the hint cut the work by about 40%, which feels completely right. Knowing where the exit is should help. Remember that feeling. It is about to fall apart. One quick thing before the big one. If you are enjoying this, a like really does help the channel. And subscribe, because what happens next is the reason I made this video. 500 across, 500 down. 250,000 rooms. Here is how the work has grown so far on one graph. 9 rooms, next 100, next 2,500. And now watch the axis rescale, because everything so far is about to vanish. The fair one goes first. It floods. It has no information, so it opens everything nearby before anything far away. 142,000 rooms. That is more than half the maze. And here is the route it came back with. 43,000 rooms long. The two corners are under 1,000 steps apart. If you could walk in a straight line. The actual corridor between them is 43 times longer than that. Now the clever one, the A-star algorithm with its hint, it floods too. 140,895 rooms. That is a saving of 1%. 1%, all of that cleverness bought almost nothing. So what went wrong? Nothing went wrong with the algorithm. The hint went wrong. The hint says the exit is under 1,000 steps away. The truth is 43,000 steps away. The guess is not slightly off, it is off by a factor of 43. An algorithm that trusts a guess that badly wrong is doing extra arithmetic for no reason. So here's the real lesson, and it is worth more than any of the four. A heuristic is only as good as the map is honest. A maze is the most dishonest map there is. Every wall turns a straight line into a lie. What does an honest map look like? It looks like this. Same size, the same 250,000 squares, but now it is open ground with obstacles scattered across it. That is a map in a video game. That is a warehouse floor. That is a city. And on a map like this one, the straight line is very nearly the truth. Same four algorithms. Same two corners. Here we go. The fair one floods again because it still knows nothing. 194,000 rooms to walk 999 steps. The committed one wanders off. 11,000 rooms opened. Far less work. But look at the route it handed back. 9,857 steps. So it escaped, and it took nearly 10 times the walk it needed. The greedy one is astonishing here. 1,176 rooms. That is 166 times less work than the fair one. Its route is 8% longer than the best one. Close, but not the best. And now the A-star algorithm on an honest map for the first time. 11,061 rooms. 17 times less work than the fair one. And its route is 999 steps. The shortest one that exists. That is the win. Not the fastest one. The only one that got both. So which algorithm won? If all you want is speed, the greedy one wins, and it is not close. If all you want is the best answer, the fair one never loses. The A-star algorithm is the one that refuses to choose between them, which is why it is the one running inside your games, your robots, and your maps app. With one condition, and it is the thing to keep. It only wins when the map is honest about distance. Give it a maze, and the most famous algorithm in pathfinding is worth 1%. Somewhere out there is a better guess for the maps that lie, and people are still looking. Maybe one day, that person will be you.